Hello, and thank you for joining us today on this webinar, Cable Systems for the Future of Underground Transmission in North America. We've got a great webinar for you today. This is number 6 in a series of 6 webinars about the 21st century cost of underground. And what's really interesting about today is what we've looked at when we looked at the 21st century cost of underground is what is the real cost of underground today. Let's look at material science advancements. Let's look at planning and engineering and construction and operations and maintenance. But today we're going to look at the HPFF transmission system. That's a high-pressured, fluid-filled, underground, high-voltage transmission system in America, in North America. And what's happened is over the last 50 or 60 years, that has served us well in many major metro areas, and it's come to end of life. So what is the industry doing to respond to that and to be able to replace these HPFF systems? So that's what our webinar is going to be about today. It's going to be really interesting. It's brought to you by the Power Delivery Intelligence Initiative. If you've been with us on previous webinars, you know that PDI Squared is a group of contractors and vendors and consultants and manufacturers that are advocating for underground, or really we're advocating for the evaluation of underground versus overhead, because we believe that the 21st century cost of underground is in fact coming down. You remember when PG&E just announced that they're going to spend $15 to $30 billion on undergrounding only 10% of their transmission and distribution system. The CEO pretty much said we can't afford not to do this. So it's a great time to be considering undergrounding, and today we're going to do that with some special guests from G&W and from Southwire. So with us today from G&W, and I'm going to ask both these gentlemen to introduce themselves briefly and say hello. But with us from G&W is Ivan Jovanovic, and with us from Southwire is Sharif Kamal. And I'll ask, hey, Ivan, go ahead and say hello to the audience and give a little bit of a brief introduction, if you would, please.
Thank you, Mike. This is Ivan. Thank you for this opportunity to talk about this interesting topic. I've been with the G&W for 20 years, actually, this year, and have been engaged in very many different roles, from product management to R&D to engineering, and currently I have global responsibility for cable accessories and current limiting protection devices in terms of the engineering and technology. I'm also very engaged in the industry standards. I represent US in different industry bodies in SIGRE and IC, and very much involved in IEEE standardization side to it.
Great, thank you. And you work very closely with Southwire and Sharif Kamal. Sharif, go ahead and say hello to the audience and give a brief introduction, if you would, please.
Thank you very much. Thank you very much, Mike and Ivan. I'm very honored and proud to be part of this distinguished panel. I'm very, very excited about it. I'm Sharif Kamal, as Mike said, and I've been with Southwire for about 6 years. Been in the industry for too many years to admit. I would not date myself here, but I have a passion and experience in high voltage. I love underground and overhead and everything, but high voltage is my passion, really. And I've done a lot of work on the cables and the accessories designs and manufacturing, and also, as Ivan indicated, a member of several standards committees, very active on the ICC and the IEEE standards committees. Again, thank you very much for this opportunity, and I look forward to an engaging and an informative webinar.
Well, it's going to be exciting because we're going to talk about some of the material science advancements and some of the things that Southwire and G&W have done together to advance the technology. I'll just comment real quickly is that as we go, if you've got questions, go ahead and submit them, and we will take questions perhaps throughout but we'll try to save 15 or 20 minutes at the end for Q&A. So go ahead and send your questions in as we go. And go ahead, gentlemen, and take it away.
Thank you very much. Thank you very much, Mike. We were going to be discussing this subject divided into several sections, as you see here. Ivan will present a short introduction of high pressure fluid filled or pipe type cables in general, and then we would see why would we need to replace these if the need comes, and how can we do that. After that, we will delve into a new hybrid system that we are developing, and hoping that you would find it interesting and useful. And finally, Ivan will close us with what's next, where to go from here. So with that, I would ask, I pass it to Ivan.
Thank you, Sharif and Mike. So a little bit about high pressure fluid filled, and I know that many people that are on call now are very versed in that. But the interesting thing and important thing about pipe type or high pressure fluid filled systems that involve cables, terminations, and joints is that really North American underground transmission was built on it, and it's been in operation for, in some cases, 50, 60 or more years, and it has excellent track record, very reliable, and it's going to be here for a while. It's not going to just disappear, but as this system ages, there needs that need to be fulfilled. There are parts of the system that need to be maintained and replaced. There is probably over 4,000 circuit miles on transmission voltage class 69 to 345 in North America. The system is pressurized to 2, 3, or 400 psi. Fluid, it can be either the electric fluid or gas. And some of the advantages are listed here. It's suitable really for all areas, not just metropolitan, but it's ideal for urban areas where you have not required wide corridors. It's very rugged and reliable pipe, and as we mentioned, asset managers, utilities who have that in their grid, they really love it because of that.
Sharif, what would be some major cities in North America that have really big, extensive pipe type systems? Just off the top, can you name a handful of them?
Yeah, definitely New York City. Yeah, definitely New York City is one of the biggest consumers or biggest utilities. Con Ed, Consolidated Edison. Chicago has a lot. Public Service in New Jersey has a lot. Transmission, Wisconsin in the name ATS. There are Encore has some in the south. So there are a lot.
Boston area.
PG&E.
Of course, they have a lot.
PG&E also. Yeah. PG&E has a lot. So yes, those are the major. Washington D.C. Washington also has a network of high pressure fluid fill. Yes.
Yeah, basically
Go ahead, Ivan. Continue.
Yeah, the northeastern U.S. has probably the largest density of generally transmission underground and specifically pipe type cables, and that's where the most of the users are even today, but other parts of the nation as well.
Yeah.
Good. Thank you.
So a little bit more about this process and what we are seeing in last, let's say, 5 to 10 years. So this aging pipe type infrastructure that consists of pipes, miles and miles of pipes in the ground, and then auxiliary equipment like reservoirs, pumping stations, and so forth, requires attention as it ages. And some of the things there to look at, there are limited numbers of contractors that can install and really work on that specialized systems, which is quite different than solid electric ones. There is one cable manufacturer and several accessory suppliers in North America. And industry faced with that is looking for different options to maintain these systems and to maintain reliable power delivery without breaking a bank, and then in the same time to mitigate any negative aspects of conversion activities and so forth. And with that, I think we are ready to hear from you guys in terms of this is the first polling question. You're going to see on the screen.
Okay, so as the audience gets to take a look at this polling question, you got about 4 or 5 seconds to read this and respond, and then I'll look forward to hearing from you guys maybe a little bit about you showed that nice cross section of what a pipe type system looks like, and maybe you're going to do this a little bit later, but you're going to explain some of the components that are in there specifically in that cable. And that cable is a paper cable, and it's something that's been around for a long, long time, but maybe just for the layman, you could explain what that looks like. And then let's take a look at what our poll results are, and we'll take it from there.
Yeah. So while we're waiting, Mike, this cable is really is relatively simple in construction. It has a conductor, and typically it's a copper or aluminum, and then some kind of an insulating medium that is wrapped around. It's either paper or, as Ivan is going to talk about, is going to be some kind of advanced paper layer, and that's it. That's what it is. Part of the paper on the outside is conductive, just to fulfill the requirements for the electrical stresses. And typically they wrap these papers with skid wires, with wire, so that they can pull them into the pipe without damaging the paper. So they kind of glide on the pipe on these wires. We call them skid wires. The paper, as we all know, is an insulator, but it is not as good as an insulator. And it has pores in it that would cause, under electric stress, would cause what we call partial discharge, and finally the failure to the cable. So to mitigate this issue, we pressurize, we embed or impregnate that paper in a dielectric fluid. And to maintain the operation, this dielectric fluid has to be under very high pressure. Minimum is 200, or nominal is 200 psi, but it can go to a much higher values because of the slopes and the distance, how long is the line between the pumping stations. The disadvantage of this, of course, is that if the pressure goes away, if the oil is lost, the cable loses its function. You cannot operate the cable without the oil.
Right.
So that's how, in a nutshell, that's how the cable works.
That was a great nutshell. That was really a good overview. So I don't know if folks can see the results from the polling question, but 45% of the audience said that corrosion and fluid leaks from the HPFF pipes are the most critical considerations, followed up by about 25% that said requirement for higher ampacities. So thanks for responding to that polling question, and let's move on, gentlemen, to the next slide. And that next slide is to talk about various strategies. Right, here you go.
Yes, so just a quick comment on the polling. That's basically what we are hearing from the industry as well, that that corrosion and fluid leaks are very important for asset managers, obviously, from the operational and environmental perspective, and that's some of the drivers that we have for to look into replacement or at least doing something with the existing lines. So if we look at last, again, 5 to 10 years, what asset managers are been looking at, it can be roughly grouped into those 4 different categories. So this first one is traditional and proven approach, where cables and accessories, terminations, joints are replaced with the same oil impregnated kraft paper when they reach end of life. This type of replacement was the most common one until the introduction of laminated paper polypropylene, or LPP, which leads us to that second approach, which was very, very popular and still is. And it came with the introduction of LPP as an alternative to kraft paper. In some cases, LPP can reduce cable wall thickness by up to 50%, and therefore one of the polling answers, 25% of people said that they need to increase the ampacity, and that's exactly what this method does by using the larger conductor in the same pipe type infrastructure. So very popular and cost-effective method that provides the benefit of utilizing existing pipe type infrastructure, including all the auxiliary equipment, reservoirs, pumping stations, and so forth. And majority of maintenance and replacement projects in North America today utilize this technology. So it's still going strong, and it's going to be there for a while. The next one that people are looking at increasingly is the replacement, partial replacements of, say, of an ailing oil sector to replace that with a new, while the rest of the circuit would remain oil field. So basically that would be a transitional replacement section by section. And for that, transition joints from a pipe type or self-contained liquid filled paper cables to extruded cables are required. And there have been a number of projects, a lot of those internationally, also in US in recent years, that utilize this approach. And this is especially true for self-contained fluid-filled cable systems that have less constraints than the pipe type that we are talking about today. The last one there is really the holy grail of replacement or retrofit in North America. So this approach is it's in infancy, where the vast majority of underground transmission infrastructure is with pipe type cables. And the main challenge of this method is exactly what some of the pollers did, answer to match the ampacity, or in many cases to have a higher ampacity than existing pipe type cable, and still fit those three extruded cables into existing pipe type infrastructure, which really eliminates very costly excavations, and other interruptions to the general public. So there are a couple of pilot projects in recent years that have been completed, but still more information and field experience is required for us to come to the full adoption and market acceptance of this. And
so there's a question from the audience right along those lines. So is anybody putting in new high-pressured fluid-filled systems today, as opposed to any of these other strategies? Is anybody putting in something brand new?
Yes, I believe so. There are utilities, especially Northeast, who are still relying on high-pressure fluid-filled cables, and there have been projects in recent years in regard to that.
Okay.
Yes, that's a good question. But talking about this full conversion, so one of the emerging solution is what we are going to talk about today, is development of, you can call it a hybrid cable system that combines, reliable, well-known pipe type components with the extruded components, extruded insulation system, customized components, XLP, and then elastomeric stress control, silicone rubber parts for joints and termination. So that's going to be our focus today.
So taking it from here is actually ties very well into the poll results. As you saw, people by far thinking that oil leaks is the problem, and oil leaks is something interesting. It will get you on the 8 o'clock news, not for the good reasons, but it will get you on there. So people, public and the utilities, don't want to have those oil leaks, and so how to avoid oil leaks with an aging system that you cannot control from the point of view of age. I mean, it's aged. It's the earlier lines have been installed since the late 30s. That's a long way back. So let's think or imagine if we were to design a system that does not suffer from oil leaks, that would save the cost of the fluid itself and the repair and the replacement of the fluid when a leak happens. That will eliminate the need for the pumping stations and the reservoirs and the monitoring equipment and the maintenance and the sampling of the oil and all this. What would that look like? Well, Ivan he actually said it outright. It's an XLPE or a solid dielectric in general system that does not require all this. And there are so many ways to do that. It can be that we make a new trench and make a system that looks like any other system, XLPE system, for example, at the higher voltages. Or what if we can use the same infrastructure? What by mean infrastructure is the same pipe. So we remove the oil-dependent cable in the pipe, and we put another extruded dielectric cable in its place. Well, there are this is a possibility. These are the earlier attempts to do that. We will just take a standard regular XLPE cable, put it inside. Well, what comes with the design of an XLPE cable, a standard one with screen wires and link boxes and bonding schemes and all this comes disadvantages, comes losses. Remember that this pipe is actually a steel pipe. Steel is magnetized or magnetizable. If you put an electric field or magnetic field close to that steel, it would actually generate eddy currents and losses. And where does the losses come from? It comes from the supply. It is the power that you want to transmit to the load. It is being consumed. So if we were to use that steel pipe, we would cut on the cost millions of dollars. We're talking millions, in some cases tens of millions, actually in most cases tens of millions of dollars of excavation, traffic control, building new duct banks, pulling the cable and so on and so forth. I already have a corridor underground between vaults that are already that exist. If I can thread a cable inside, I get rid of most of these costs. Now, are there going to be places where I would need to dig and fix? Absolutely, but not the entire trench, not the entire the noise, the traffic control, the safety concerns, all that goes away if we use the already existing infrastructure. Also, as I said before, with standard XLPE in a duct bank, there are bonding schemes that are really, I could say, complicated and requires certain provisions that if we use the pipe, all this goes away. If we can mimic the system, the original system, the pipe type cable, and use the pipe, that will simplify the solution significantly. And finally, because the old system had the oil in it and it's old, with the new system comes the possibility of actually inserting fiber optic cables with that to determine the temperature along the line, so we can spot hot spots or trouble areas before actually failures take place, and also the vibration. So if somebody is digging around that cable, around the pipe, we know that there is somebody digging into this area. So if we can design a system that would work this way, it would be a fantastic improvement to the industry. And with that, I guess we are ready for the second polling question. And,
okay, we'll give you about 5 to 7 seconds to respond to this. That was a great overview. We're probably going to have to move a little bit faster because we're 25 minutes or so into this, and we've got a lot of content left. I will ask you to make a quick comment about oil versus dielectric fluid or filling fluid. And do we really want to refer to it as oil? Because there's a question from the audience that, hey, is the EPA requiring utilities to make these changes because of the oil, when in fact it's really an inert filling fluid, more like a mineral product than anything else. It's used to pressurize the paper cable.
I would say, go ahead, Ivan. You know this.
No, that's okay. I'll chip in later. Just go.
I was just saying that it is probably the right terminology is fluid and a dielectric fluid. It's not an oil per se. It's just the way the old folks like me used to call it. So anything that soils your clothing and you can't eat after handling it, we call it oil. So that's probably a better terminology. It's a dielectric fluid. If anyone,
okay. So about 50% of our audience. Go ahead, guys.
Yeah, that's exactly. I couldn't said it better. It's the electric fluid. Young and old folks call it like that, oil sometimes, but it's really inert, the electric fluid. And I don't believe there is any. I'm not 100% sure, but I haven't heard from any EPA regulation that would require this. The only problem that happens with this when there is a leak, right? So that's really where the regulation stepped in. But other than that, it's perfectly fine to have this in a closed system circulated under the pressure.
Okay, so about 50% of the people on the survey said full conversion to solid dielectric cables, terminations and joints in existing pipe type structures. They picked C by about 50%. So thank you for responding to that. Looks like replacing aging cables was at about 21%. So, okay, well, so moving on to the next slide, gentlemen, take it away.
Yes, so I will. The next slide is just to tell you what are we going to do. What are we? This was the vision. We wanted to convert the dream into reality. So realize the dream is our need. The goal is to develop a system that would work. And the steps for this development is to envision the system and then do desktop verification, simulations, make sure that things work on paper, and then convert the theory into practice. So design the components, the cables, the accessories, joints and terminations, and all the other accessories in the system. Manufacture these parts or the prototypes, and then finally testing them and implementing them in the field. So that's the process that we were going to go through. And with that, there was a big team assembled for this. EPRI, EPRI and the Underground Transmission Task Force had a great input into this. Of course, these are a bunch of very, very smart and experienced people who got together. They actually developed a concept and they patented it. And the patent was granted in about a couple of months back. And those are the main thrusts behind the whole project. The Southern Company was a part of the transmission task force, and they are also part of the invention of the patent inventors. I mean, they are inventors on the patents, and they are also so progressive that they are considering or proceeding towards implementing that solution in a field trial. Southwire, we engaged with the team, and we are responsible for the design and manufacturing and installation of the system. G&W are our trusted and chosen partner, and other than friendship, of course, but they are a very competent company working on the design of the accessories and matching it with the design and manufacturing and the testing of the accessories and matching it with the cable. And then finally, Power Delivery Consultant was an EPRI consultant, and they also are patent inventors. And they are providing us and EPRI continuous technical support. With that, I will talk about the design constraints. So when we came with that concept, we wanted to design the cable. What are the guardrails? What cannot we, or we did not want to go out? We wanted to use the pipe infrastructure. This is, as I said before, it's the holy grail. Why? For all the reasons we talked about. We also wanted to utilize as much as possible existing components from the systems that are well tested, people are well familiar with, and we don't need to reinvent the wheel if the wheel is already invented. We also wanted to limit, in this particular case, to limit the stress limits in the accessories and in the cable to what is required by the AAIC, the Association of Edison Eliminating Companies, which are the consortium of the utilities in North America. So we didn't want anybody to frown on the stress limits. Not that we can't go higher, it's just not, we didn't want to go higher to start with. We wanted to make sure that the system does not require, by the law, by the standard, does not require or may not require qualifications, but testing is always welcome and will be done either because of our own internal due diligence or by the request of the customers, the users. And finally, we wanted definitely not to derate the cable, so we want to have at least the same amount of ampacity like the replaced cable, but in many cases we can actually improve the ampacity, and in some cases by far. And finally, as I said, we wanted not to invent the wheel. So as much as possible, we didn't want to impose new manufacturing techniques or equipment that would require further development. With that, we came up with the design with a cable that combines the best and the well-known of both worlds, of the XLPE or solid dielectric portion when it works, and of the power of the HPFF, whatever works for the HPFF. And so, as we said, our problem was to the oil. We wanted to get rid of the oil. Then we get an insulation that does not require oil. The conductor is the conductor. It's either copper or aluminum, and that carries the current. The insulation system, instead of using the papers, we are using a solid dielectric. In our case here, especially for higher voltage, we would use cross-linked polyethylene. And then on top of that, we put a bedding tape, and it's actually a water swellable tape too, just in case there's any moisture that goes inside here. It's not supposed to have any moisture, but in case, we don't want that moisture to extend. Now,
gentlemen, let me interject a question. Let me interject a quick question in here from the audience. One of the audience questions was, what is more prevalent, aluminum or copper? So you talked about aluminum or copper being in the conductor. What's more prevalent in North America?
I'd give you my opinion, but I don't have numbers or I don't have statistics. I believe that it's copper. In North America, people love copper. They were very reluctant to start using aluminum in power cables in general, and that's probably coming out from the lower voltage and the problems that people had with the connections at lower voltage with aluminum. So I would say copper. I'm not sure if Ivan has any different opinion.
No, that's absolutely true. Based on the inquiries from people, discussion with industry, utilities, copper is the king still.
Yeah, absolutely. So going back, Mike, to what I was saying, so the portion up till that, which is the green portion, the green square on the or whatever shape on the screen, is a standard extruded dielectric cable. That's a standard thing. What is different here is that the metallic shield. Typically, we would use screen wires. In here, what works with the HPFF is actually a stainless steel tape wound helically around the cable. And the reason for this is to reduce the losses, which makes us mimic what the HPFF is, which has been working for years and years and years and years. On top of that, HPFF does not typically have a jacket, as we talked before. It has a skid wire, but in here, they didn't need a jacket because they are embedded in oil, and the oil is a protective layer for the entire system. Here, we don't have that. Yes, it's true that the cable is going to be put in a pipe, but this pipe over years may be perforated, it's not going to have high pressure. It may corrode. It may have a seepage of water or any other liquid. To protect the cable, because not our system, our insulation system now will be very exposed to the environment, to that environment inside the pipe. If there's no jacket, we opted to put a jacket. Now, as I said, we may or may not need to put skid wires. The skid wires only allow us to pull the cable for long distances and skid inside the pipe. So that may not be needed as depending on the length of the pull and the nature of the pipe and how good it is or so on. Just wanted to highlight here that this design is what is the subject of the patent by EPRI. So that design was described in the patent by EPRI. One thing that I wanted to show here, other than the beautiful picture which shows the pot of gold at the end of the rainbow, it is because we are putting a lot of cable inside this pipe. We want to maximize the ampacity. This means that we have the minimum possible insulation thickness. This means that the concentricity or the centrality of the conductor within the insulation is really, really important. This is guaranteed or facilitated, not guaranteed, but facilitated by using a vertical extrusion line or vertical continuous vulcanization process, which, as you see in this tower here, this is not a smokestack. It's actually an extruder line put vertically, and that allows the cable to, or the process to eliminate the damaging effect of gravity, which is something that we have to live with. Just as a matter of bragging, we would be able to produce cables here with less than 5% eccentricity as described by their standard. I think give it back to Ivan. Ivan, you want to talk about the joints and termination?
Thank you, Sharif. That was all about the cable, right? So once Southwire and their partners come up with this design and approached us, we of course need to marry that with cable accessories, and those are obviously critical components of the system. And some of the specific design considerations that we had to look at are listed here. Physical constraints are very, very important if you're trying to fit something into the existing infrastructure that in some cases is built like 50, 60 years ago. Wall dimensions, and we also considered 2 lines per circuit, which is often the case in North American utilities. The installation consideration, sequence of parking components, bringing those components in the vault, welding of the casings and other pipe type components, and then really looking at the thermal and mechanical stresses. So we are, and as you will see, have the closed system of 3 solid electric phases without forced cooling option. So that's a change from pipe type. And then how to clamp, how to support, how to look at the thermal stresses and how to address those. So with that, G&W team has designed and come up with this beauty. So it's and just to make clear, this is not part of the patent that Sharif talked about, which pertains to cable. So, but this does work with that cable. So what we have here is basically a 3-phase composite joint that consists on extruded components like the pre-molded, factory tested silicone rubber joint bodies, and well known and proven but modified for this application pipe type components like you can see the casings and pipe reducers and so forth. This design is also optimized for installation in small vaults and vaults that have 2 lines per circuit. And we have also the feature of mechanical shrink installation for those pre-molded rubber joints that really allowed us to design for those constraints. Another thing here are those integrated internal mechanical supports with spiders and clamps to secure both joint and the cables. And as you can see, everything is encased in a fully sealed system that consists of welded stainless steel casings, pipe reducers, and other components that can be gas pressurized, and it will be probably in a pilot project to keep the moisture out. We also have additional option for jointing fiber optic cables, and that can run from one substation to another with the option of having DTS, communication, disturbance monitoring, and so forth. So talked about joint installation. You can see a typical arrangement that can be found in North American high pressure fluid filled valves, where you have basically active line here with a joint, that this bigger casing, and then another line that, for example, can be replaced or retrofitted with this hybrid solution. So for that, what we have is the mechanical shrink installation method that I briefly described on a previous slide. And here it shows basically the difference. So the traditional slip-on method on the top picture, in that case, your rubber body needs to be parked on one side. Everything needs to be connected in the middle. And then the system of, say, clamps and pullers need to be put on the other side. And then everything needs to be centered later on. So a lot of time, a lot of opportunity for mistakes in a field in this harsh environment, and also a lot of space. For mechanical shrink, you don't need tools. You can park it, and then just when you're ready to position it, you can pull the cord. So that's one of the features that really benefited this design. In terms of the termination, we really used the existing proven and tested design, proven in the field for many years, of the fluid fill termination with the elastomeric stress control, pre-molded and fully factory tested in our factory per IC and IEEE standards. And then the bottom here is really redesigned and changed. So what we have here is a different clamping system, and also pipe stub, similarly to the pipe type cable. So that's where we marry those two technologies together in order to connect to the cable pipe, which goes all the way to the top, and then to hold and secure that. In this case, we opted for lightweight composite insulator that's shown here, that seals the cable and the stress cone, and also provides the striking and creepage distance in air. So we had the cable. Sharif talked about that. We had termination. We had the joint. So we had all the ingredients to make a test loop and see how everything works together. So the test program was really custom designed by the team that Sharif showed. All of those different entities and people, very, very smart and experienced people, participated in design of this custom program. The first part was done at Southwire, just on the cable itself, routine and other tests that Sharif is going to talk about. And then parts 2, 3, and 4 were done at G&W lab, high voltage lab in our headquarters in Bolingbrook. So one of the things that we talked about are installation tests. So we wanted actually to try dry run of installing those joints, mimicking the real field conditions, and you'll see some pictures from there. The next tests were really cable pulling. We needed to pull those 3 cables in a pipe, and we had a real live pipe that we had in our lab. And also the important thing obviously was to do initial temperature analysis. What should be the current, what should be the temperatures, and how to hit those US higher temperatures of 100 to 105. And then the last set of tests were the electric tests, main test loop. They were basically integrating IC, AIC, and ICA standards. There is no current standard for this type of a system or a product. So we worked closely with the potential end users, with EPRI, and came up with this. And notably, we did use 100 to 105 degrees C per US standards, which is a requirement in North America. So with that, we have another polling question. that actually we would like to get your input on the standardization requirements, which is very important for developing this market forward.
Okay, so as folks take a little bit of time to respond to this, a couple of questions from the audience, and we're kind of running out of time here a little bit, but this topic is fascinating. A couple of questions about grounding and the role of the steel pipe in grounding of this new proposed system. Do one of you want to respond to that real quick as we wait for the poll results?
Yeah, I'll take this if you don't mind, Ivan.
Sure.
The idea of this system is that it's a hybrid system. So whatever is working from the original HPFF, we will continue to use. Whatever is new from the new system, from the XLPE, we'll use. So we are using the same scheme for grounding that is used in the standard HPFF systems, which means that the pipes, this is a multi-grounded system, and the pipe is going to carry the short circuit currents. We do not need additional wires or screen wires or anything to carry the short circuit to carry the short circuit current. And the pipes are going to be designed, or the system is designed to maintain the cathodic protection of the pipe. So again, like an old HPFF system.
Good. Thank you. Go ahead and push those survey results out, and it looks like almost 50%, about 48% of the people said US and IEC standards, and then about 20% said C, the IEEE standards for cable terminations and joints. So thank you for sharing that. We appreciate that.
That's very good input that we are going to consider, obviously, going forward. This is a little bit of uncharted territory, and we'll talk a little bit later about that. So, Sharif.
And there were some people, about 20% of the people said new standards to be developed.
Yeah,
that's an option too. Absolutely.
Yeah, absolutely. Thanks for that input. That's really important, particularly for both Ivan and myself and our colleagues who are working on these standards, because we are charting, or we are walking uncharted territory. Just very fast, I just wanted to talk. Obviously, when you make a cable, you have to do routine testing, and I just wanted to say that it has been done according to the cable standard, the U.S. cable standard, ICA, electrical and physical quantities. It's very standard. We also did the pull test, the pulling test that you have talked about, but we also did a bend test, which is pre-requirement or a prerequisite for the type testing that we have performed that Ivan is going to talk about. And those two pictures here showed how do we bend the cable in 180 degrees, top and bottom, to actually make sure that the cable is mimic the hardship that the cable goes through when it is being put on the reels, transported, and put into the ground. So that's a standard part of the testing. And with that, I'll shoot it back to Ivan, talk about the installation.
Yeah, thank you, Sharif. The next set of tests were done at G&W Bolingbrook plant, and you can see here with Southwire installers actually coming to do this installation test. So you can see one of the pictures there. On both pictures, actually, we mimic the line, the proximity of the live line that you saw on the wall picture, and had the constraints of the actual physical constraints of the actual volt, and then try to install those three joints together, park all the casings, and do all of that. And of course, in theory, you have something in your mind, and that's why you do this type of practical trials in order to adjust that. So we had a lot of good input and changed accordingly our design and installation procedures. So the last part of the test was the main test loop. So you can see here the rendering of that test loop that was done in our lab, the footprint and everything else. You can also see the section of the steel pipe that was delivered from Southwire to us. That was part of the loop per the really requirements that we had from the project team, and that's also where we measure the temperatures. And the loop consisted of one 3-phase joint and then two outdoor termination per design that I showed. And we had, as you can see, 3 different loops. So one loop was the one that was energized, the main test loop. The other 2 loops, one was what we call the dummy loop for measuring the temperature, and the last one was the third phase here, which was a spare loop in case of interruptions that we could resplice that. We didn't have to do it, but it was there. Really, the goal, the driving goal there was to induce, in all 3 cables to induce the current like it would be in a real application, which is really quite different and novel to any of the existing high voltage cable or accessory standards. And what would that do? That would give us the proper thermal stress, both in a pipe and then in a joints and everywhere else in a cable that we measured. And also in addition, we were able, due to the very inventive approach of our lab manager, to come up with a way how to induce the real 120 degrees offset current, so the real 3-phase one. So we had all of the ingredients to mimic as close as possible the real life situation. Those are some of the pictures of the main test loop. You can see the way how the joints were assembled here, and then we even brought the external contractor that would do the also welding in a field to try out, to see, measure the temperatures, making sure that everything is good there. And then the picture of the loop with 2 terminations and this joint in the middle are shown there. With that, I'll give it to Sharif to talk a bit about the test program. Hello, Sharif, do you want to talk about the test program?
Oops, sorry, I had to happen once in every conference. I was on mute. It has to happen. I was going to say that this is the test program. The innovative thing about it is that we combined all the testing per IEC, AIC, and ICA in an overarching program to cover all the bases. So we are the cable and the system testing from American and international standards. Nothing special other than everything, of course, passed. It was great. And with that, what's next?
Yeah, the next step. So that's really what's exciting. So this is one of the first projects like this, and the implementation of the system in the field pilot project that we are after would be the first step there. So we are really excited to work with people, with the end users, with asset managers to do that, and we have one pilot project in mind. After that, really, it's about how we scale this up, right? So this was done for one specific configuration, pipe type configuration, and then the question would be, what are going to be different combinations of pipe sizes, cable sizes, and so forth that can fit into different options that utilities have in North America. So scaling that up. And really overarching mission, I think, for the industry and for our companies and PDI Square is to really implement this solution in years to come, to really reduce the cost of undergrounding, and also to mitigate those negative aspects of construction, excavation, and everything else that goes with the conversion. So that's kind of that concludes this this project or the next steps for us.
Well, gentlemen, that was really interesting. We have dozens of questions, so I'm going to jump right into it because we got about 7 minutes left. But fascinating topic. So where was that question that I wanted? There was a question about supporting the pipe supporting the cable in the pipe. So how is the cable actually supported in the pipe itself, in the steel pipe?
The cable is not supported in the pipe. In fact, it is floating in the pipe, and that causes some of the constraints on the design. The cable, as you know, is made of metal and metals or material solids, and the solids expand with the temperature. So as the cable is being loaded, it will expand, and the only thing that is supported is the joints at the vault on each side of the pipe. So the cable is free to move in the pipe.
Good.
Free is really, between inverted commas.
And what is the maximum? Another question from the audience. What's the maximum voltage for these joints? The joints that you guys were showing.
These joints were tested, were geared actually for a pilot project and were tested 115 kV level. But the maximum voltage for these tested joints is 138 kV, so one level up. And as we are showing here on this last slide, we are looking. We don't see the reason why we wouldn't be able to scale those designs for higher voltages.
So in your evaluation here, have you picked a utility that you think you're going to be able to go and test some of these patented designs on?
As shown in one of the earlier slides when I showed the project team, actually Southern Company, which is the utility headquartered in Atlanta, Georgia, is going to be our first, or at least we are hoping that they will be our first pilot installation. They are part of the team. They are actually part of the team.
That would be a pretty good place to start, for sure. Okay, I think that I have gone through all these questions from the audience and we've answered most of them. What I want to do in the last 3 or 4 minutes that we have here, gentlemen, is give you each a couple minutes to say some concluding remarks, tell the audience thank you, and wrap up with whatever your conclusions are on this really interesting HPFF alternative product that you got.
Go ahead, Ivan.
So, Ivan, why don't you go ahead?
Sure, thank you. Well, this has been a ride for us. We collaborated on that for the last 2 years, and had many different options to go and different routes to take. And I think we chose the very good one. And really, as we said, we are hoping that this will help the reducing the cost and helping at the end asset managers, utilities, construction companies, general public with bridging the gap of our current transmission underground system and reducing the overall cost over the period of time. So it's obviously very, very critical with the integration of DERs, we hear about a lot of activity offshore wind on the Northeast. We heard about strategic undergrounding on distribution side. So the industry is changing and rapidly, and we hope that this is going to be one important ingredient going forward. Sharif?
Thank you.
I echo this. Yes, sure. I echo this sentiment. Just want to make sure that it is very, very exciting. And the excitement for me personally is that we are offering the industry an alternative. We are offering the industry a solution that would make them less puzzled and less stressed. Nobody is wanting to replace the HPFF systems, the perfectly good and operating systems. But when the need comes, it offers an alternative. And it's an alternative that is hopefully equally or better. It is more economical than the available alternatives, and it provides them with a security of supply. So this is exciting. It's been a ride, as Ivan said. We are very, very excited about it, and we look forward for a great success for the industry as well as for our companies. Would like at the end also to thank you, Mike, thank the PDI Square group, thank the support, thank Southwire and GNW for their support to us, because without the support of everyone involved, we would never have been there. I would like to have a shout out to the project team again, the EPRI, the Southern Company, the PDI, I'm sorry, not PDI, Power Delivery Consultant, PDC, and to my colleagues at GNW. So thank you very much, everyone. Thank you, Mike, and thank you, Terry, for the opportunity.
Yes, Sharif, well said, and Ivan, I thank you as well. You know, we talk a lot about innovation in our industry, and I think here's a great example of GNW and Southwire and EPRI and the Southern Company getting together. Power Delivery Consultants certainly really came up. This is a very innovative idea. We have an asset. We have this pipe type system, and at some point in time, like Sharif said, we will have to replace those cables, and you guys have come up with a really great concept here that is exciting. So credit to both your companies and to your team, and I think you guys really are doing a good thing here for the industry. Looking forward to getting out and seeing this next year, maybe at an ICC meeting or maybe at the big IEEE Power and Energy Society Expo. So anyway, hey, on behalf of GNW Electric and Ivan and Southwire and Sharif, we thank you very much for listening in today. Thank you from the Power Delivery Intelligence Initiative. We appreciate you listening to this 6-part webinar series on the 21st century cost of underground. That cost is coming down both in materials science and design and construction and operations and maintenance, and hopefully we've shown you that. This webinar will be available on the PDI Squared website, along with all the other, and also on T&D World. So thank you to the folks at T&D World as well, and I wish you the very best. Have a great and safe and productive day. Take care.